Now, lecture 13, spherical coordinates. Elements, let's put a plural here. Element of volume and element of length in R3. Attention now, extrinsic geometry. So, in this case, this is a particular case of curvilinear coordinates, okay? Because this is spherical coordinates. Don't forget to go back part 3, lecture 4, okay? So this is there we initiated this spherical coordinate, okay? Now, the objective here is to obtain the element of volume and element of length in R3. Element of area we'll do the next lecture, okay? Now, let's start from this figure over here, okay? So this figure over here is an element, okay? This is the orange, okay? This is the position vector, that's point P. And this over here, you see the diagonal here? This is a point Q. So it's clear that R depends of C1, C2, and C3. You see, in this case, P is the origin of this curvilinear coordinate. Okay? Attention now. dr is an element of the position vector. Okay? Is a differential. Now we can express dr over here, okay, as the sum. Clearly, I can tell you to come from here, okay? You just come from here, okay? So the element dr, okay? This is attention now. This is a tangent vector to the coordinate C1, which is R. Okay? This one is the tangent vector to the coordinate phi. Okay? And this one is the tangent vector to the coordinate theta. You just look at here. You see, I just transport from this figure right over here. See, this here is point P. You see point P here? So these are the basis vectors, okay? A1 is partial of R, the blue one, with respect to C1. A2 is a partial of R with respect to C2, and A3 is partial of R with respect to C3. Now, we derived the previous videos that the spherical coordinates, okay, we have there attention now, orthogonal basis. It's not orthonormal. We could obtain orthonormal, just divide, okay, each base by its magnitude, so you get the unit vector. But now we are working here. We found on the last video the metric, the covariant metric 1 R2 and R2 sine phi square, okay, in the denominator, okay. This over here, okay, it's attention now. Gij, Ci, attention now, Ci, okay, here, you see these indices, they are, in this case, okay, the upper indices, but the derivative, they appear in the denominator, see, which is important, see, they appear in the denominator. So I is covariant. I over here is contravariant. Likewise J. Okay? J, the denominator, is in this case covariant. J over here is contravariant. So we define Gij, you see? Gij is just the dot product between AI dot AJ. See? This is Gij. So here we derived the previous video, okay, and we can obtain dr dot dr, okay. So this is AR, this is A phi, this is A theta, which is written over here. So if I obtain the dot product of this vector with itself, knowing that we have in spherical coordinates, we have orthogonal bases. That's why Gij, they only have different from 0 in the diagonal, okay? The diagonal is different from 0. So for I different from J, Gij is 0. So that's, you see, G11 is 1, G12 is 0, G13 is 0, and so on, okay? That's clear. Now, I just changed the notation, okay, for clarity, okay? G11, GRR, G2, G phi is equal R2, you see, it's over here, and G33 is G theta theta, this is R2 sine square, okay? I just wrote from there, I wrote here. Now, you see the inverse, okay? This is contravariant, okay? I just take the inverse. Inverse of 1 is 1. Attention now. The inverse of R2 is 1 over R2. And the inverse of G theta theta is 1 of R2 sine square. It's quite easy. I can do this because the inverse of a matrix, okay, when you have a diagonal matrix, the inverse, I just get inverse of each term on the diagonal, okay? Now, one very important result, okay? Square root of G, we already did this, okay? Is the mixed product. This is dot product, this is cross product. We call the mixed product. This is exactly the determinant of Gij. Oh, the determinant of Gij, I just multiply the diagonal elements here, which will be R square is R4. So 1 times 1 is 1. You see, that's clear, okay, what we are doing over here. Now, attention now. Square root of G, we already proved this, okay? This is also is interesting from the previous video, lecture 12. We did like this, okay? Also, we obtained the square root of G is this mixed problem here, okay? We derived in lecture 10 in part 7, lecture 11, I think. Now, then I have G, okay? You just R4 sine square. You look at here, okay? You just multiply. See, R square is R4, and this will be the sine square is over there. Now the square root is R2 sine phi. You see, the square root is R2 sine phi. So the element of volume is already here, okay? In this case, it will be I square sine phi dr d phi d theta, which is dx1, dx2, and dx3. Okay, just quite clear, okay? Because C1 we set equal to capital R, and in this case C2 is phi C3 is theta. So that's quite clear. So you already obtained the element of volume. Okay, let's continue. You see, the length square is dr dot dr. Attention now. Dr dot dr, okay? This is, attention now, this is A sub r. This is A sub phi, this is A sub theta, okay? This is exactly, if you multiply this vector by itself, we already obtain, you just look at here, okay? That's quite easy, okay? Attention now, this figure here corresponds to the spherical coordinates, okay? Because this x over here, the basis vector, they are orthogonal, okay? So, attention now, r here is a function of capital R, okay? This is not working, okay? Capital R, this is phi, and this is theta, see? This I just redefine, okay, this just to use the notation, Einstein notation, okay? So you substitute this by this, okay? Like for instance, okay, AR by A1, A phi by A2, and A theta by A3, okay? Then I can use easily this relation over here. Now ds squared dr dot dr. You see, ai dot aj is gij. So then ds squared is gij dxi dxj. Attention now, gij will be 0 when I will be different from j. You see, because the system is spherical, the bases are